Welcome to lecture 12 in our class on stochastic processes, and today we will introduce Brownian motion, which is a universal and very important model for the motion of a molecule, if you like, which diffuses in space in a random fashion. And therefore it appears in almost every field of applied mathematics or physics. If you like, it's very important. It's also very important as a model for the motion of a stock price on the stock market. Today we will introduce this stochastic process, this class of stochastic processes, in fact, in a constructive fashion, because the axiomatic definition of a Brownian motion composes a couple of non-trivial properties, or requires the existence of an object which has very distinctive stochastic properties, and it's a priori not clear that such an object exists as a mathematically rigorously definable object. And our work of today will be to actually demonstrate that our intuitive interpretation or intuitive understanding of what such a Brownian motion could be, that this actually is of substance in the sense that there is a mathematical object which satisfies these conditions. Okay, so we start with the intuitive interpretation or the intuitive picture of Brownian motion. So the name of this process as Brownian motion goes back to a biologist, Brown, who observed pollen in a liquid and under the microscope, and he realized that this pollen, so these little pollen pieces, do perform a random motion. They fluctuate, and they are performing a motion which is called Zitterbewegung in some fields of physics, with the German word Zitter, which means oscillate. So it's a process which oscillates in space. And of course we would like to have some statistical description of this process in addition to certain path properties of this process that we would want to require. So here you see three different possible realizations of such a pollen in this liquid that this biologist could have observed. All these three possible realizations are equally likely and perfect simulations. Suppose you start the pollen at the origin or the center of this three-dimensional domain, and then you let it evolve. So the idea is that it has a certain temperature, or it is embedded in a liquid where it collides with other pieces or other molecules of this liquid, and these liquids push this observed pollen around, and you observe, therefore, this random motion. And as I just said before, these three plotted realizations of the resulting motion are equally likely and perfectly possible as curves that this, or as trajectories that this pollen is performing. Now, if you project these curves into one of the coordinates, so for instance, you project the red curve onto the motion regarding only the first coordinate, what you see is an up and down movement, and that would be a perfectly chaotic up and down movement. And if we want to avoid the possibility of sudden jumps, which would really produce macroscopic jumps from one position in space to another, we would simply have a chaotic up and down movement by one step size if we discretize with regards to the spatial resolution. And so in the end we would probably see a curve like this, which is this chaotic up and down movement. And here you see that the projection onto the respective coordinate axis already give an object which we kind of understand, because this looks like a nearest neighbor random walk in just one dimension. So the trajectory of a nearest neighbor walk, when this is time and this is the integers, or the lattice z, on which this simple random walk can do its motion. So, in other words, the motion in here 3 coordinates can be thought of as an independent superposition of motions in each of the coordinate directions, where each of those motions is of this type. And here in the graphics you already see that this is not claiming to be a Brownian motion, but here in the headline it already says that the Brownian motion that we are supposed to describe here is in fact here generated through an approximation by random walks if we choose to observe the random walk for a sufficiently large amount of time and scale the spatial resolution accordingly. So in today's lecture we will formulate in an axiomatic fashion when a stochastic process, which in this case is running in continuous time, when a stochastic process will be called a Brownian motion. So we will give an axiomatic description of this, and then we will show effectively by constructing such a process that it exists, that this axiomatic definition of a Brownian motion is not empty. Brownian motion can be constructed, and the way that we shall construct it is exactly through scaling of nearest neighbor random walks on the integer lattice. And as we will do this, and as we will conduct this program of today's lecture, we will encounter and partially also prove some quite heavy and very important mathematical theorems from functional analysis and probability theory in general. So let me say it again. The agenda of today is an axiomatic definition of Brownian motion and the proof that Brownian motion processes exist, and we shall do this. We shall prove the existence of Brownian motions by an approximative and constructive proof. Namely, we will show that if we scale in an appropriate fashion the nearest neighbor simple random walk on the integer lattice, then this will lead us to a realization of Brownian motion. One of the 2 main ingredients in order to show the existence of Brownian motion, and I shall say this even before I have told you what we shall understand by Brownian motion, but one of the main ingredients for the existence of Brownian motions to the proof is the central limit theorem, which is of course one of the most fundamental theorems in probability theory. Let me recall to you once more the statement of the central limit theorem. It goes like follows. Suppose you have a sequence of IID random variables which have expectation 0 each, and which have, say, variance 1. Then you can take the partial sum of the first n realizations of this sequence of random variables xi, so it's just the aggregate sum, if you like, of wins and losses in the respective rounds, and you divide this by square root of n, when n is the total number of summons which enter this partial sum. Then, if n tends to infinity, this sequence of random variables converges in law, or weakly in law, to a standard normal distribution. What does that mean? Convergence in law can be defined as follows. It says that if you compute the expectation of this random variable, when you combine this with an exterior continuous and bounded function, so you evaluate this expectation of this random variable, the sequence variable, through a continuous and bounded observable, then this sequence of expected values for a given observable f converges to the integral of that observable f with respect to the standard normal distribution. So convergence in law says that the expected values converge to the expected value of the claimed limit when we evaluate the expected values with all kinds of continuous bounded functions. This is a special case or another instance of the following saying of the following concept in probability theory. So if you have a sequence of, say, Euclidean random variables, so random variables assuming values in the Euclidean space, then you say that the sequence of these random variables converges to a random variable x infinity weakly if the corresponding expected values converge, where the expected values are taken by means of composition with a continuous bounded function. So in that regard, this convergence of these scaled partial sum variables towards the standard normal distribution is exactly an instance of this convergence of weak convergence of random variables, because here the random variable that you would pick here would be any standard normally distributed random variable x infinity. So convergence in law to a given random variable is just the same as saying that the collection of laws of the corresponding random variables, which are supposed to converge to a given probability distribution. That's why sometimes weak convergence of a sequence of random variables is also sometimes called convergence in law. Okay, so this central limit theorem is one of the two most important theorems in probability theory, and I suspect that you have seen some proof of this theorem already in the past, either for the binomial distribution, where it's called the De Moivre-Laplace theorem, and it goes back, I think, already to the late 18th or beginning of 19th century or even earlier. And the modern versions are less restrictive regarding the assumptions on this collection of random variables psi I which enter. And it says in a way that the standard normal distribution will appear naturally as a natural constant if you just sum up independent trials of the same experiment, and if you normalize the whole thing in such a fashion that it becomes expected value 0, has expected value 0 and variance 1. This is exactly why we chose this scaling, because in this scaling, this corresponding sequence of random variables will have expectation 0 and variance 1, just as the standard normal distribution. And whenever you do the scaling in such a fashion and you pass to the high n limit, to the large n limit, then this collection of random variables has a universal limit regardless of the further specifics of these random variables psi I, and therefore the standard normal distribution is so important because it's so robust. It appears basically regardless of what you put in, provided you scale properly, you will arrive at the standard normal distribution. And if you look at this from a physical perspective, it says that the net influence of a independent sum of pushes, of up and down pushes, if you scale for constant variance 1, then this sequence of independent pushes will converge to a net randomness, to an overall randomness, which is just described by the standard normal distribution. And why am I highlighting this so much in the context of this pollen dynamics? Well, if we really think that the pollen is moving through the influence of the pushes by other molecules, which we do not see, by smaller molecules, so forth, then we would probably think that the infinitesimal motion of this pollen is somehow described by a random variable, which is standard normal, because that would be somehow the net effect of all these individual chaotic pushes which act on this pollen, but if you like, on a final resolution such that we cannot detect individual pushes, but we see only the aggregate effect, which then should be somehow a standard normal behavior that we can observe on a macroscopic level. Okay, so the simple limit theorem is an essential ingredient for the construction of what we shall later define as a Brownian motion. And we can now use this central limit theorem already for a first statement regarding the large time behavior of the simple random walk on the integer lattice. And the statement goes like follows. So if you consider just the simple random walk on the lattice, so the things that we have discussed already in the context of Markov chains. So it's just the motion of a Markov chain which has the integers as state space and which starts in 0 and which does an up or down movement at each moment of time independent of the past with equal probability. And then if we fix a collection of time points t1, t2, and so forth until a capital time point, capital T, or Tn, I should probably get it right, this is the Tn. Let me write this as a Tn. So some terminal time Tn so I fix a collection of time points t1, t2 until tn, and I evaluate this Markov chain at these different time points through composition with certain test functions or observables f1 to fn, but I do not observe the random walk alone, but I apply some scaling. So the scaling that I apply is that I multiply the time on the time axis, I accelerate in a linear fashion by not evaluating the Markov chain at time t1 alone, but at time n times t1, n times t2, and n times t3 and so forth. So I accelerate time effectively by multiplying the times at which I evaluate through the factor n, and I do not leave it alone with the acceleration of time, but I also divide the process by this scaling factor square root of n. So it's the same scaling factor that we had just seen in the central limit theorem, which was here. So here, if you think of it again, so a simple random walk is basically a sum of independent pushes up and down. And what we do here in terms of a simple random walk, we do not evaluate the simple random walk at a particular time n alone. We divide by the square root of n in order to observe something in the limit which is meaningful. Okay, so we do the same. We evaluate this Markov chain, but now not at one particular moment of time alone, but at a collection of time points, which are the time points t1, t2, and tn. And then I evaluate all these time points with a linear scaling factor n that would stretch the time axis significantly. So I evaluate effectively this Markov chain at very late moments of time. And since I expect very large values, I would probably want to divide by square root of n each of those individual observations before I actually plug them into this test functions fi. And then the statement here of this theorem is that if I let n, which is the scaling factor here, it's the scaling parameter, if I let the scaling parameter tend to infinity, then the corresponding sequence of expected values converges to an expected value which involves just a proper collection of independent normal random variables. Namely, for f1, the f1 function is evaluated on square root of t1 times eta 1, where eta 1 is a standard normal distribution. The random variable, the observable f2, is evaluated on the same square root of t1 times eta 1, which appeared already before, but I add a square root of t2 times eta 2, and so forth, so until the latest evaluation, which is an evaluation by means of the function fn. And here I will have as the random variable, which needs to be inserted into this fn function, square root of t1 eta 1 plus square root of t2 minus t1 correction. And here I made a mistake in this here. I'm sorry for that. So here that's poorly written, and in fact it's wrong. So what needs to be written here is just first term is just right. So I have a square root of correction. I have a square root of t1 eta 1 plus square root of t2 minus t1 eta 2. So I take the difference of the two time points t2 and t1. I take the square of it, and that needs to be multiplied as a prefactor to an eta 2, and so forth. So here I get this product of these increments for Fn, where all these etas, eta 1 to eta n, are independent standard normal random variables. Okay, so let me say it again. I take now a simple random walk, and I evaluate this simple random walk at different time points. But before I do that, I stretch the time axis by a linear factor n, and I divide by square root of n the process or the value of the trajectories. And this will be the different random variables which I want to evaluate by means of a collection of test functions. And here in this evaluation I had a certain parameter n, which was the scaling factor. So I applied a linear and time scaling, and I applied a square root in space damping scaling. So that's what is called the hydrodynamical or diffusive scaling of this simple random walks. It's a particular scaling regime which I choose. And the statement is that this sequence of combined evaluations of this process, when I take the scaling parameter to infinity, will converge to a combined expectation of independent random variables, where I have a hierarchy, if you like, of these increments which need to be inserted into this sequence of test functions corresponding to this different points of evaluations when the functions needs to be computed. And that's, as we shall see in a minute, a more or less straightforward consequence of the central limit theorem, which we had just repeated, which is a standard result in classical probability theory. And we shall see in a minute that this more complicated statement is in fact a slight generalization of the central limit theorem when we apply this to a sequence of evaluations which we perform on the same sequence of independent random variables. We shall see now why this is a more or less straightforward consequence of the central limit theorem, which we had just written before, namely that just in order to see this, we need to clarify a little bit of wordings and saying in this. So assume we have n sequences. So we have n sequences of random variables. So you have one sequence x1k, where k is the running index. You have a second sequence x2k, and you have and so forth until you have an nth sequence. So you have n different sequences of random variables, where each of these random variables, for all j from 1 to n, converge in the sense that we had just discussed, namely in weak sense, to a certain random variable x star with the corresponding index. Then I can consider the sequence of random variables, which then will be Rd valued. And I can just write them as a joint array, if you like, or it's just one Rd, or correction, Rn valued sequence of random variables. Then this Rn valued sequence of random variables will then converge weakly to an Rn valued random variable, which is just the composition of these independent random variables. That's a straightforward consequence of the concept of weak convergence. Okay, and once we have this corollary, we can now really understand why the, if you like, multi-time central limit theorem is actually true. Namely, let us do the case that n equals 2, so we just have two possible times of observation. So I have two functions f and g, and I have two time points of evaluation, t1 and t2, where I want to do the evaluation. And I forgot to say that if I write this this bracket here, this floor bracket, this is meant to indicate that I take the integer part. Well, here I'm talking about the simple random walk, which is a process which is defined only for integer time parameters. So if I want to do this scaling with respect to the time variable, I need to project down to an integer value time index, which is done by just concatenating to the integer part. Okay, so let us now consider or indicate how we prove this, if you like, multi-time central limit theorem. Well, so we have this combined expectation, and there we recall that for the simple random walk can be represented as the realization of a sum of up and down movements. So x, t1 of n, and so forth is just this sum of xi k, where xi k is going up and down. It's just this sequence of Bernoulli random variables. And the second part here I write as a sum of the corresponding two truncated sums, namely xt2n, of course, since it's the simple random walk evaluated at a later time, is the simple random walk at the previous time plus the sum of the remaining pushes which are obtained in the intermediate time. And if I denote each of these random variables which appear there, these truncated or non-truncated partial sums by xi n or theta n, then it's just an expectation of these xi n inserted into the f function and the sum of xi n and theta n inserted into the g function. So this is, abstractly speaking, just a slightly more complicated function in two variables, which is evaluated on this tuple xi n and theta n, where this function f here on two variables is defined as the product of the little f times the little g evaluated at s and s plus t respectively. And by the previous lemma, we know that this now deals with two independent sums of independent random variables which all converge according to the central limit theorem. So to this first term here, to xi n, I can apply the central limit theorem straight away. In the second term, in the second summand, I have a sum of the first plus an independent part. So to each of those, I can apply the central limit theorem, and by the lemma, I know then that the joint evaluation of the two random variables then converges to the corresponding joint evaluation of this two random variables, and where xi1 and xi2 are independent. So I see that I obtain exactly the statement that in the limit, this expected value is nothing but a composition of two, is an expected value which involves the proper combination of two independent standard normal Gaussian random variables where they are multiplied with a prefactor in such a fashion that the variance matches the variance of the approximating sequences. And for n greater or equal to 3, the proof is done in completely analogous fashion. Okay, so what have we learned from this corollary? We have learned from this corollary that if we evaluate the simple random walk at different times, and if we scale in this very particular diffusive fashion, namely we scale time in a linear fashion and divide by the square root of the scaling factor, that's again called the diffusive scaling, then this sequence of evaluations in the sense of expected values converges to an evaluation which involves stacked standard normal random variables. So if you look at this looks a little bit like the position of, it's not like, it's just in a way, this first This first argument of the function f1 is basically the position of the scaled random walk at time t1. And this second argument for the second function stands for the sum of the position of the scaled random walk at time t1 plus the displacement that has taken place, or that has occurred, in the time step between t2 and t1. And this displacement, so this perturbation of the position at the previous time point, is a standard normal perturbation, but it is scaled with respect to the time gap in such a fashion that the total variance of this perturbation with regards to the two different points of observation is linear with regards to the time gap. And so this logic then is perpetuated also for the next evaluations. So if you like, in Fn, the evaluation of Fn involves the position of the scaled random walk at time tn minus 1 plus a perturbation for the displacement in the time step from tn minus 1 to tn, which is again an independent standard normal displacement, but the actual displacement is scaled in such a fashion that the variance, so the fluctuation, the uncertainty regarding this latest displacement is linear with respect to the time gap that we have in between the two observations. This is already a very nice and intuitive interpretation of what is actually this scaled random walk. The scaled random walk here in this diffusive scaling regime is something that is really normal, and everything you observe at a certain time is basically the superposition of independent pushes, where the independent pushes in between time points are again standard normal, scaled in such a fashion that the variance or the uncertainty is linear or is proportional to the time lag that you have in between two points of observation. And that's now exactly our basis for the axiomatic definition of Brownian motion, which will be a process which is continuous in time. So it's a stochastic process which has the full non-negative integers, the full non-negative real line as time parameter. And we call such a process xt, which is defined on a probability space omega fp, a Brownian motion, a one-dimensional Brownian motion in this case, if first almost all trajectories are continuous. So with probability 0, we observe actually a jump. So the molecule cannot disappear at one moment of time and reappear at another point, at another moment, in one time step, or one infinitesimal time step. It cannot all of a sudden disappear at one position and reappear at another position. So no jumps are allowed for the trajectories, which is another way of saying that for almost all realization of the path, the corresponding path, so the motion, is a continuous motion in space. Second, the process has independent increments, so it has independent displacements. And if you fix any finite collection of time points where you want to observe the process, then you can look at the different displacements that you observe in between the corresponding pairs of time points. This will be a sequence of, in this case, n plus 1 random variables, and you want that this are independent random variables. So in other words, the displacement that you observed at a previous time interval will have no statistical influence on the displacement that you observe in another time interval. Of course, the actual positions will be related and there will be correlation, but the changes of the positions, when you compare the position of the molecule on the pairs of boundary points of the time intervals, these displacements are independent. And finally, what you want is that the two observations which you can make in between two time points as a displacement, as one of such a displacement, these are standard normal distributed random variables with mean 0. So in mean, the process does not change its position at all, but it has a statistical it is a statistical quantity, so it is randomly distributed, and it is distributed with a random. It's distributed with a probability measure, and the distribution is just a standard normal distribution with expectation 0 and variance given by the size of the time lag in between these two time points. So whenever you have a process x, which is defined on a continuous time scale, and which satisfies these three properties, namely continuity of trajectories, independence of increments, and that the increments are standard normal distributed with mean 0 and variance equal time length, then this is called a Brownian motion. If we additionally require that the initial position is 0, then this process x is called a standard Brownian motion. And finally, a process which assumes values in d-dimensional space is, if that's a stochastic process which is that we want to study, if it is so that each of the coordinates are one-dimensional Brownian motions, then we call this process a d-dimensional Brownian motion. Okay, so this definition, this axiomatic definition of a Brownian motion, is satisfied by, for instance, by two different approaches. One is, if you like, a physical intuition behind, which we had tried to discuss, namely that there is this random perturbation or this random motion of this molecule, and it diffuses in space, and since these pushes on a lower microscopic level, say, are not observable on an individual fashion, we just do this aggregate thing, there we arrive at the central limit theorem, therefore we want that the displacements evolve in a normal fashion over time. That's one way how to justify this axiomatic definition. And the second, already almost foolproof, if you like, except a few very relevant and deep details, which I shall present subsequently. The second justification would be this multi-time step central limit theorem, which we had discussed, that if we scale a simple random walk, at least on the level of this, what we say finite dimensional distributions, we have convergence to exactly such a process, which has these increments, this independent increment structure with exactly the Brownian or standard normal statistical increments. Okay, once the axiomatic definition of a Brownian motion is accepted, it is not at all clear still that we can actually find Brownian motions as mathematically rigorous objects. And all the rest of this lecture today, lecture 12, is devoted to prove that we can actually construct Brownian motions. In fact, there's many ways how you can construct Brownian motions, and you will encounter probably several of those in the future. And we want to give in this lecture today a full proof, which is really based on this idea that we apply a diffusive scaling to a simple random walk. And the critical question in most of the constructions is the question whether you can construct such a process which has also continuous trajectories. So the innocent requirement about continuity of trajectories is the one that poses the biggest mathematical challenge if you want to convince yourself that such a process actually exists. And we will invest now quite a bit of theory in order to convince ourselves that this scaling of a simple random walk actually leads to a Brownian motion which in fact generates continuous trajectories, which is probably not so obvious from the start. And this will be done by looking at this convergence of processes in an abstract fashion as a framework to, or we develop a framework of convergence of processes in the case that we deal with processes which are continuous, which have continuous paths right away. So we need a concept of weak convergence of random variables in a way which assume values in the collection of continuous paths. We will introduce a second type of path space. So remember that in the context of Markov chains, we already introduced the concept of path space, which was the all possible paths, so all possible sequences, infinite sequences, which assume values in the state space. And now we shall do a similar thing, but now the collection of paths that we want to consider will be the collection of all maps which map non-negative time into a state. So suppose you have a state space, again, like in the situation of Markov chain, suppose we have a state space S, which now does not need to be countable. So for instance, the Euclidean space of dimension D can be such a topological space, or a state space, and we want to assume in fact that this space is a topological space, which means that we have a concept of open sets. And tau here is this collection of open sets. So in other words, we have a concept of convergence. In RD, which is our most important example, we have, of course, a concept of convergence. The sequence of points in RD converges to another point if all coordinates converge to the corresponding coordinates of the limiting point. So that gives rise to a notion of convergence or a topology. And now we want to consider the collection of the path space, which is the collection of all continuous functions which map the non-negative real line into that state space. So it's exactly the collection of all these red, blue, or green curves, if you like, that we have seen. So each path here now, if you like, that's our new canonical path space. Each of this little omega is one possible continuous trajectory. It's the space of all continuous paths. And we want to now we'll talk about convergence of random variables which assume values in the collection of continuous paths. So for that, we would like to equip this set of continuous paths again with a topology. We say that a collection of paths or a sequence of paths converges to another path in this path space if for all finite times capital T, we have convergence with regards to the supremum norm on this compact time interval of this collection of paths omega n to the path omega. That's what we shall understand as convergence locally uniformly in time. So we say that omega n converges to omega if omega n as a sequence of functions converges to the function omega in the sense of locally uniform convergence. This is exactly what this says. And we can also put a metric on the collection of paths which exactly metrizes this topology. Namely, we say that the distance between two paths, omega n and omega, is this weighted sequence, this weighted sum of supremum norms, where we truncate the supremum for convergence with one, but on each of these growing and increasing intervals, we take the supremum between these two trajectories, omega n and omega, and this is then multiplied with the converging factor 2 minus k. And it's a simple exercise to show that we have convergence of omega n to omega if and only if this metric between the two, namely the sequence and this possible limit point, is a convergence sequence. Hence, we have now a metric space, namely the space of all continuous functions which assume values in S, which is equipped with a metric D, and it's again an exercise to convince yourself that this is a complete separable metric space, which means that it is a complete space, so Cauchy sequences have a limit. It is separable, which means that there is a countable set of paths which lie dense in this collection, in this set. Yeah, and that's when we call a space complete and separable, or a short name for that is the Polish space. So we have a complete separable metric space, and we will now discuss the concept of convergence of random variables which assume values in this complete separable metric space. Okay, we have a concept of a topology, so we have put a topology on the collection of continuous paths, assuming values in a topological space, and we shall use as the topological space S, or the state space of the stochastic process now the real line, say, and with all these concepts at our disposal, we can now formulate the main result of today's lecture, which goes as follows. So for each n in the integers, consider the stochastic process xn with the upper index n, which is in continuous time, non-negative times. Namely, xn of t is 1 over square root of n times xnt, so it's exactly this scaled random walk. Whenever the time t at which you evaluate is a multiple of 1 over n, and in all other time points, we just take the linear interpolation. So in other words, we have this up and down movements, or I should write that as an up and down movements for these integer times, or times which are multiples of 1 over n. And what you do in between, you just draw the linear interpolation between. So that's the process xnt. So it's exactly this accelerated process that we were dealing with at the beginning when we were talking about this multi-time central limit theorem. Now for each n, xnt is a continuous process, so the paths of this construction are all continuous. And if we now take this scaling parameter to infinity, then the statement is that this sequence of processes, which is understood now as a sequence of random variables which assume values in the collection of continuous paths, so it's a random variable with values in the continuous path space, then this weak limit, which exists and is unique, it is namely uniquely determined as the law of a standard Brownian motion on the collection of paths. So, in fact, this theorem has two statements which are combined into one statement. Namely, one is that the sequence of random variables, of continuous paths valued random variables, has a limit, which then is, by definition, a probability law on the set of continuous paths. And this probability law is exactly the law of a Brownian motion, or in other words, if you consider the map which takes a continuous path into the evaluation of the path at a certain point t, at a certain time point t, then this is a stochastic process, and by definition it's a stochastic process which is continuous, and the law that we put on path space by this limiting procedure then will generate a Brownian motion. So in other words, there is a unique limit of this collection of scaled random walks, and this unique limit is in fact a law of a Brownian motion, which means that it is a probability measure on the collection of continuous paths, and the distribution which is obtained by evaluating the trajectories at different time points, this finite dimensional distribution is exactly the distribution of a Brownian motion. This measure W, which we obtain on the collection of paths, is called the Wiener measure, named after an Austro-American mathematician, Norbert Wiener, who lived in the first 2/3 of the 20th century. Okay, the proof of this theorem, which is, as I said, the main theorem of today's lecture, goes in 2 steps. First, we show that this collection of random variables is compact, or is pre-compact in the sense of weak convergence. Namely, we say that this sequence of processes is so that it allows for subsequential limits. So it's pre-compact with respect to weak convergence. In other words, every sequence of this sequence of continuous path valued random variables contains a weakly convergent subsequence. That's the first part, its compactness. And the second part is the identification of all possible limit points. So it's a uniqueness statement about the limits, which then altogether says that the entire sequence converges to a unique limit, and this unique limit then is also a model for a Brownian motion. Okay, so the most difficult part, after we have settled the multi-time central limit theorem, is the existence of a weakly convergent subsequence, or the compactness. And since we have chosen as the topology on the set of all continuous paths the topology of local uniform convergence, it's a not complicated exercise to show that in order to prove convergence to a weak limit, it is sufficient to fix an arbitrary time point t and show that for all such possible finite time points we have convergence of the collection of laws to a limiting law when we restrict the time parameter to this finite time interval. If we have such a convergence, then we can just concatenate all these different convergence statements of the respective time intervals in order to obtain a full convergence on the unbounded time interval. This is just a consequence of our topology that we chose of local uniform convergence. So therefore, it is sufficient to restrict the discussion to a compact subset of the time axis, namely from 0 to capital T, and make sure that on each of such chosen compact subsets we have this convergence and we have uniqueness of the limit. Then by just, if you like, passing to capital T to infinity, we obtain the full statement. Okay, so for that reason we fix a finite maximal time parameter, and we shall work now with the topology of uniform convergence of continuous paths which we put on this collection of uniform paths. So that's now a perfectly fine separable metric, complete metric space, so it's a Polish space. And we want to show that this sequence of scaled random walks, which we interpolate in between the rational times by continuous interpolation, this sequence of random variables, when suppose we restrict to the time from 0 to capital T, that this the corresponding induced laws are compact in the sense that every sequence contains a weakly convergent subsequence. And for that purpose, we shall now introduce the first very famous and big theorem of today's lecture, which is very important in a lot of situations, which goes like this. So if we have a sequence of Borel probability measures on a Polish space, and if it is so that for any positive delta, we find a compact set in this topological space, such that all measures of this sequence mu n of the complement of this compact set are no bigger than delta, then mu n contains a weakly convergent subsequence. So let me say it again in slightly other words. So suppose you have a sequence of probability measures on a Polish space, and suppose that for arbitrary tolerance level delta, you find a certain compact subset of this topological space, that the measure of all these sets mu n is effectively concentrated on this compact set. up to error delta. Then this collection of, or the sequence of measures, probability measures, contains at least one weakly convergent subsequence. So that's a compactness theorem or a compactness criterion for a sequence of probability measures on a Polish space if we work with the concept of weak convergence of probability measures. The converse statement, by the way, is also true. It's called Prokhorov 2, if you like, a second convergence, namely if we have convergence of a sequence of probability measures mu n to mu in the sense of weak convergence. Then for all delta positive, we find a compact subset in S such that this sequence of probability measures gives basically no weight to the complement of this compact uniformly up to error delta. Here in our lecture today, we shall only use the Power Theorem in one direction, namely as a criterion which we need to verify, or which we can verify in order to guarantee existence of weak limits after choosing a proper subsequence. So the Power Theorem is very important. It will appear in many instances if you look up a paper about complicated stochastic models. Then the first thing to be studied, and which is typically studied in those papers, is the existence of reasonable models. And this idea of proving compactness and uniqueness is very often used. So, and the Power Theorem typically appears there in one or the other fashion. And that's why we want to sketch the proof. We go in two steps. Namely, first we want to assume that the space is compact to start with. In this case, the compactness, or this Prokhorov condition about this delta, almost entirely exhausting compact subset is superfluous. And here then we claim, in fact, that any sequence of probability measures on a compact state space is relatively compact, so contains a weakly convergent subsequence. And since the collection of bounded functions on this space is separable, we find a countable collection of continuous bounded functions that for any other continuous bounded functions we can find a subsequence phi k prime from this collection of points which converge uniformly to F. Now, by a diagonal sequence, using the fact that all the integrals of mu n against one of those test functions phi k is bounded, so by a standard diagonal argument, we then can subtract iterated fashion subsequences such that this sequence of integrals of a fixed test function, a fixed function from the basis, from this countable subset, tested against or integrated against this test the measure mu n prime, where n prime is a properly chosen subsequence, such that this converges to a certain function L of phi k for all possible k. Now it's easy to check that this L of phi k is a linear function also, because it's basically coming from a linear sequence of functionals as a limit point. And so then by density of the test functions and the boundedness of the integration against the uniform norm, we find that there's a unique continuous bounded linear functional which maps the continuous bounded functions into the reals. So there's a unique continuous bounded positive functional which is just obtained by taking the continuous extension of this functional L using the density, the fact that this collection of phi k functions is dense in the collection of test functions. And now we invoke the Riesz representation theorem, which tells us that this continuous bounded positive functional is represented through an integration against a uniquely determined probability measure, in this case a probability measure on the set S. and it's therefore a well, in this case, then it's just a tautology to say that the mu n integration of phi, or mu n prime integration of phi, will converge to mu n of phi, basically. Is now an immediate consequence. Okay, if S is not a compact set, then we now will invoke the Prokhorov condition, which is our departing point, which tells us that for all positive tolerance values delta, we find a compact subset in S such that the measures give weight to this compact subset up to an error delta. And here we do this in an iterative function. We namely choose a sequence of delta L for L running in the integers, which converges to 0 such that for each of those L values we find a compact subset. And without loss of generality, we can assume that this collection of compact subsets is increasing. So we have a sequence of increasing compact subsets, which up to basically negligible error in terms of measure, exhaust the entire space S. And then we can again do a repeated subsequence argument or diagonal argument in order to convince ourselves that for each of these compact subsets KL, we have a certain measure mu L, which is defined on KL, on the compact subset KL, such that mu n prime restricted to KL will converge to mu L, to this measure mu L. And moreover, since this sequence mu n prime is obtained by taking subsequential subsequences, we also find that if we restrict this measure with index L plus 1 to the subset KL, then we obtain the old measure mu L. So we have a consistent hierarchy of measures, and hence we define for every set, measurable set E, or Borel set E, on the state space S, we define mu of E to be the limit when L tends to infinity of E intersected with KL. Now, by the previous upwards consistency property of this sequence of mu L, this is a consistent definition, and this defines a measure on the set S, and by the construction it's also evident that this is a probability measure, namely mu of S is 1, because the total weight of the complement must necessarily be 0. Okay, and now we want to convince ourselves that we actually do have weak convergence, so let phi be an arbitrary bounded continuous function. And for L in the integers, let now we want to make a localization argument in order to convince ourselves that we have convergence for these integrals. So let phi be integrated with respect to a measure mu n prime, where n prime is this properly chosen diagonal subsequence. Then we can decompose this integral by means of a multiplication with an indicator function of this compact subset. So just by multiplying and the indicator function and its complement onto phi, we can decompose this integral into these two pieces. Now, mu n prime, when integrated against a function which is with an indicator on the set KL, is just as good as if we restrict the mu n prime to the KL subset. This is the first little remark that we make, and regarding the second summand here, we just realize that this total integral which we have here on the right hand side is a quantity which is bounded by, in absolute value, by a function which is of the order of the supremum of phi, which is bounded by definition, and delta L, which is the total size, if you like, or the total tolerance level for the compact set KL. So which means this thing here is no bigger than phi, the indicator function of the complement of the compact set KL times the supremum norm of phi. So therefore this term here is bounded like this. And now for n prime tending to infinity, by the property that n prime converges when restricted to KL to mu KL by this consistency. This converges to the integral of phi with the indicator of the compact set KL against the measure mu when restricted to KL. This term remains unchanged. And again, we can write this by the definition of the measure mu. We can write this integral of the indicator function multiplied with phi as just an integral with respect to the full measure mu, which we had defined above. There's just a rewriting there. And again, we can smuggle in the indicator function of the complement of the set KL and use the same argument as above to convince ourselves that the difference between the full integral of phi against the mu and the integral of phi when integrated against the KL is maximally of order delta L, so that we get this error term at most twice in the end. So in the end, we find that this limit superior when n prime tends to infinity of this difference of these two integrals is bounded from above by 2 times the supreme norm of phi times delta L, where L was arbitrary, and hence we can send L to infinity in order to convince ourselves that this convergence is actually true. Okay. So that proves that if we have such a uniform concentration, if you like, of the sequence of probability measures on a compact set, which was this Prokhorov condition, was this condition here. So if for any tolerance level delta, we can find a compact subset in this Polish space such that the sequence of probability measures is concentrated onto this compact set uniformly with a uniform error delta, then this sequence of probability measures contains a convergent subsequence which converges to some probability measure on the state space S in the sense of weak convergence. This is what we just have shown, and the critical argument here effectively was that the collection of bounded continuous functions on a polar space is separable, and we have used in essential fashion the Riesz representation theorem, which says that the dual space of the continuous bounded functions on a compact subset, on a compact set, is given by the set of measures, or probability measures in this case. Okay, that's the Markov theorem, and this is what we shall use in order to show that this sequence of random variables, which assume values in the collection of continuous paths, which is a polar state space, that this is in fact pre-compact or with respect to the topology of reconvergence of measures. Before we actually apply the Prokhorov theorem, we want to highlight one piece of lingo here. So we say that the family of probability measures on a topological space is tight. Tight, that's the technical term which is sometimes used in the probability literature to describe this uniform concentration on a fixed compact set, if and only if exactly this Prokhorov condition is satisfied, namely for all positive threshold values or error levels delta, we find a compact subset such that the probability measures concentrate on this compact set up to an error of maximal delta. So if that's the case, then we call this family of probability measures tight. So, and Prokhorov theorem just is paraphrased by saying that a tight sequence on a polar space contains a weakly convergent subsequence. Okay, now finally we want to apply this, or we want to use this abstract Power theorem in order to produce a criterion which will guarantee that the collection of laws of a collection of random variables, which is some values in the collection in the set of continuous paths, when this is tight, when this is precompact. And we shall use a tightness criterion which is derived from the Prokhorov theorem in the particular case when the polar space is the set of continuous trajectories. And this is the so-called Aldous tightness criterion. So David Aldous is a contemporary American mathematician. And the theorem here goes like this. A family of stochastic processes which all have continuous paths, and we want to assume here for a moment that the time parameter space here is restricted to the compact interval from 0 to t. This collection of random variables, which assume values in the collection of continuous paths, this induces a tight family of probability measures. So the corresponding laws, which are now probability measures on the set of continuous trajectories, this collection of probability measures on the set of trajectories is tight if the following two conditions are satisfied. First, the corresponding family of initial laws as a family of probability measures on the d-dimensional Euclidean plane, if in fact we talk about a collection of random variables which assume values in the set of continuous paths. So we have now, let me say it again, we have now a sequence or a family of random variables which assume values in the set of continuous paths. And we can ask ourselves, is the corresponding family of induced laws, so induced laws on path space, is that a tight family when we work with the topology of uniform convergence on the set of paths? And the conditions by Aldous that guarantee the tightness of this collection of probability measures are two. Number one, we want to check that the collection of initial laws of this probability measures, or these stochastic processes to be precise, is tight in its own right. And the second condition we want to check is slightly more complicated to formulate, or it's certainly more complicated to formulate. Namely, we want to make sure that for all possible tolerance levels epsilon, the following uniform convergence in probability holds true. Namely, we want to consider for each possible stochastic process I, we want to consider the probability for the event that for two given stopping times, sigma and tau, which are sigma stopping times relative to the process xi, relative to the filtration generated by the process xi, and when these two stopping times do not differ by more than a certain time lag delta, and all these stopping times are assumed to be less or equal than t. So we want to consider the event that the stochastic process xi has a difference, changes its value by more than epsilon in the time interval between sigma and tau, when sigma and tau are two arbitrary stopping times. Provided that the difference of the two stopping times is no bigger than delta. So we want that such a probability converges to zero when the time difference, the possible difference between the two stopping times sigma and tau, converges to zero, and this probability should converge to zero uniformly with regards to this collection of stochastic processes and uniformly with respect to the possible choices of all stopping times which satisfy this condition. So if that's the case, if we can verify this, then the collection of laws of this family of stochastic processes with values in the continuous path, then this is a tight family. By the way, here in this formulation, we assume for a moment, when we write a P out here, we assume for a moment that all these stochastic processes are defined on the same probability space omega fp with a common probability measure p, but this directly generalizes to the case when we actually have, for each of these stochastic processes, we have a different stochastic base, as we say. We have a different probability space omega I fi pi, on which the respective stochastic process xi is defined. So in that case, we would just replace the pi here, the p here by pi. Okay. Now, why? So before I want to give details about the proof of this Aldous theorem, I want to give an indication why this condition is true. Well, if the collection of laws of a stochastic process is tight, then certainly the evaluation of the process at certain time points, individual time points, should be tight, because it's just a continuous projection to a lower dimensional subspace, and that should be basically consistent with our concept of weak convergence. The second condition, which is this seemingly very technical condition, basically says that the probability of having large jumps in this collection of stochastic, in these trajectories, or large fluctuations in the trajectories, this is becoming uniformly small when the time interval in which you want to observe such large jumps becomes small. So this is effectively a bound on the fluctuations of the stochastic process. And the reason behind this bound on the fluctuations is the Alzira-Ascoli theorem, which is a sufficient condition for compact subsets in the set of continuous functions. Recall that a collection of functions on a compact subset is basically, or is compact or pre-compact with respect to uniform convergent, basically if and only if it is uniformly continuous. And this is exactly the content of the Alzira-Ascoli theorem, which I want to formulate here in the given situation. And suppose you have a certain subset of continuous functions which assume values, or which take values in the Euclidean space. Then this collection of functions or trajectories is compact with respect to uniform convergence on the interval 0t if the starting points of these trajectories are in a compact subset of Rd. And finally, if this collection of paths is uniformly continuous. Uniform continuity of this collection of paths can be formulated as follows. Namely, for all possible time points s and t, which are no further away from one another by delta, the evaluation of the trajectories on these two different time points converges uniformly among all these trajectories from this collection of trajectories A to 0 when the distance between these time points tends to 0. That's what we call typically uniformly continuous. So that's saying that the trajectories, the differences of the trajectories on two different time points become uniformly small if the time points on which you make this comparison of the two values become small, if the difference becomes small. That's what we call uniformly continuity, and it's uniformly continuous because we take the supremum with respect to the collection of trajectories inside. Okay, that's our criterion, or that will be our criterion to identify compact subsets in the set of continuous paths. And now, what's the relation of this with respect to the Prokhorov theorem? Well, the Prokhorov theorem says, okay, if you find a compact subset on which the probability measures uniformly concentrate for arbitrary precision level delta, then this collection of random variables or probability laws is tight. And for that, in order to apply this abstract Prokhorov theorem in our given situation of continuous paths, we need to make a proposal how this compact subset should look like, and in order to make a reasonable proposal, we have to check that the actual set which we propose for a given precision level delta, that this proposed set is actually compact. And in order to make that, to justify that, we will use the Ascoli theorem in the way that I have just stated it. So we need uniform continuity, or we'll check for uniform continuity in the context of Prokhorov theorem and in the context of Ascoli. Okay, and another way to formulate uniform continuity is by looking at what is called the modulus of continuity of a given curve, namely the modulus of continuity for a given level delta of a given curve is exactly the maximal difference you can see between two different evaluations of the curve when the two different evaluations are no further away than delta. That's a certain number which depends on delta, and which, of course, depends on the trajectory, on the function which you evaluate. So again, the modulus of continuity of a certain trajectory is given as the maximal difference of two evaluations of this trajectory when the two evaluations are no further than delta apart. And to say that a collection of sets is uniformly continuous is just as good as saying that the modulus of continuity converges to zero uniformly when delta converges to zero. Okay, and suppose now that for a given level delta, the modulus of continuity is greater or equal than 2 epsilon, say, then it's easy to find stopping times sigma and tau, which are no further away than delta, such that the evaluations of these two different stopping times is at least epsilon. So basically, how you can do that, you just see, you start at each moment of time, you look back onto the last interval and compare the current value with the latest maximum or something like that, and then when that exceeds a certain number, that's the first stopping time, and you iterate this, and that's the second stopping time. And when the modulus of continuity is greater or equal than 2 epsilon, then these two stopping times will produce a difference in value of at least epsilon. Okay, so let me say it again, when the modulus of continuity of a trajectory is greater or equal than 2 epsilon, then we can find stopping times sigma and tau such that, which are then no further away from one another than delta, such that the evaluation of the trajectory on these two stopping times is at least epsilon. And now we want to apply this rationale in order to convince ourselves that in fact the Prokhorov theorem is satisfied. Namely, given delta positive, we choose a sequence eta k of numbers which converge to zero fast enough such that the sum of the eta k's is still below delta. And we choose a sequence of epsilon k numbers and as well a delta k number, a delta sequence which converges to zero. In such a fashion, that the supremum for all I, the supremum of the probability over all stopping times between stopping time sigma and tau, which satisfy these conditions, that they are no further away than delta k, that you observe a difference in value of greater or equal than epsilon k half, that this is less or equal than eta k. It is possible to find such. So it's possible to find an eta k. Obviously, that's just a fast enough convergence sequence to 0. And given this eta k sequence, finding epsilon k and delta k is possible by the condition which is formulated in Aldous theorem and which is our point of departure, which means that for every tolerance level epsilon k, we can find a delta k small enough such that this probability is really small. Now, if we introduce the subset of trajectories ak on the compact interval from 0 to t, which have modulus of continuity greater or equal than, for given delta k, greater or equal to epsilon k, then by the previous consideration that if the modulus of continuity is greater or equal to something, then we find appropriate stopping times, then we find that this collection of stopping times is a subset of the collection which are described in this condition here. So we have these stopping times, and therefore the probability for each of the measures I to find of this collection of trajectories is no bigger than eta k, because that's exactly what the Aldous criterion is now telling us, that the probability for AK is bounded from above then the probability of the corresponding stopping time event, and the stopping time event has by Aldous criterion a probability of no more eta k for all probability measures pi, which are the measures induced from this set of trajectories. Now if we take the probability of the union of all these AK sets, then by the union bound, by subadditivity, if you like, of probability, this probability for the union of these AK is, by the choice of the eta k, no bigger than delta. And so for that reason, the complement of this union, which is the collection of all trajectories omega, which satisfy the opposite condition for all delta k, namely it's the correction of all trajectories for which the modulus of continuity for all k is less or equal than epsilon k. This set is then a set of trajectories which are then this set A correction. This is then a compact set, because this is a set of trajectories whose modulus of continuity we can control in a uniform fashion, and therefore we have a compact subset of the trajectories, and we have convinced ourselves that this compact set of trajectories has a measure greater or equal than 1 minus delta, because its complement has probability no bigger than delta uniformly with respect to this parameter I, which stands for the collection of stochastic processes. Okay, so this is why the Aldous theorem is correct. So in order to check tightness or compactness of probability measures on the collection of continuous paths, we need to check these fluctuations for arbitrarily chosen stopping times. We can now finally apply all this and conclude with our main theorem. So our main theorem was the claim that this collection of scaled random walks where we apply a diffusive scaling, which is linear in time and 1 over square root in space. So if we have this sequence of stochastic processes for each n, where n denotes the scaling parameter, which, as I just said, consists of scaling linear in time and with a square root with respect to size or in space, and where we interpolate these points of the trajectory in a linear continuous fashion in between those rational points. So we want to show that that's the claim, in fact, converges in the sense of weak convergence to Brownian motion. Okay, so all these processes, for each n, they start by construction in 0. So the first of the two conditions in Aldous's compactness theorem is trivially satisfied, because they all start at one point, which is the 0 point, which is obviously a compact subset. So therefore it's a tight distribution of the set of starting points. Now, in order to convince ourselves that also the second condition is satisfied, the stopping time condition in the Aldous situation, let us make the following few remarks. Namely, if we have a stopping time which is relative to the filtration generated by this process xn, which was appearing in this Aldous criterion, then since the whole process xn is generated by this collection of up and down random variables, this is effectively a stopping time which is generated by these up and down process psi. And the second important remark is the following. So, namely, if we have, in fact, the situation that we have stopping times tau and sigma of this continuum linear interpolated process, which are no further away than a certain value delta, and which, say, differ in value by more than epsilon, then by the linear interpolation, the maximal difference we can see between two such evaluations for continuous time is basically given also by evaluating this trajectories only on the integer time points. Because everything which is in between the integer time points is just a functional of the things that happen at the integer time points when actually the randomness kicks in. So therefore, whenever we have two stopping times, arbitrary stopping times, which can assume values in any time between 0 and capital T, such that this difference of points is bigger than epsilon, then we find two other stopping times, sigma prime and tau prime, which are possibly no further away than this delta, but with a little bit of an error, because the grid size here is 1 over n. So suppose, so we can need to modify the stopping time a little bit and move forward or backward in time in order to find the corresponding grid point, which means that we have now stopping times which assume values on the corresponding grid, which are then no further away than 2 over n, so the maximal jump size of the grid of time points on which we actually work, and which are, say, no bigger than t plus delta over n, such that the same difference is obtained, right? Such that these two different closest nearby integer or grid valued stopping times, the difference between the two trajectories is again bigger or equal, or it's greater than epsilon. Again, let me say it again, why this is true. This is true because the linear interpolation between which we apply for this xn process in order to make it a continuous process is really just a very boring thing. So if we want to really measure different elongations or different differences of evaluations of the process at different time points, and if we want to ask what's the maximal difference, then it's basically suffices to do this on this integer grid points. Okay, and now if we want to make a estimate on the probability that we have for two such stopping times which are on the grid, that this probability, the difference of these two evaluations is greater or equal to epsilon, then we can insert the definition of these random variables at the two grid points. By definition, this by definition of the scaled process, the difference of the two evaluations of the scaled process at different time points involves the sum of these up and down random variables, but it will be not a sum with where we the number of summons is not given by sigma prime and tau prime alone, but due to the linear scaling in time, it's tau prime times n as the upper index and sigma prime times n plus 1 as the lower index. And the X process definition involved also this 1 over square root of n scaling in front, so therefore inserting the definition of the X process into this difference just leads to the representation of this difference by this, which involves the sum of these up and down variables. And now we can just apply a Chebyshev inequality, which tells us that this is given by above by the sum of these different variances, where this number of summons is no more than the difference of these two bounds in the sum, and this difference of the two bounds in the sum is given by delta plus 2 over n times n. That's the maximal number of summons that we will have appearing here in the sum, and the Chebyshev inequality with the square relation gives a 1 over epsilon squared times n as a denominator in this estimate. And then we see that this n function or this n number here cancels, and we arrive at an expression which clearly converges to 0 if we send delta to 0 and n to infinity. So hence we can check the Aldous condition for this sequence of continuous path valued random variables, and as I said before, since all the starting points are 0, the first condition is automatically satisfied, and hence we have that this sequence of laws of the stochastic processes is tight by Aldous condition. Now, as for the identification of the limit, we can employ the work that we had invested at the beginning of this lecture, which told us that the sequential evaluation of this scaled process at different time points converges to this sequence or to this evaluation which involves this iterated nested standard normal random variables. Maybe the same. So therefore we have a unique description, or we have a description, a unique and unambiguous description of the finite dimensional distribution of the corresponding law on path space, which means that all possible limit points of this sequence of random variables, after we took subsequential limits, which we can by the Aldous tightness criterion, so all possible limit points have the same finite dimensional distributions, but a law on this path space is uniquely determined by its finite dimensional distributions. So therefore, these finite dimensional distributions determine a unique probability measure. The measure exists as a limit of these probability measures. So therefore we have a unique limit point for all possible subsequential limits, for all possible subsequential limiting subsequential sequences, and therefore the whole sequence converges to this law or to this probability measure, which has then the right finite dimensional distributions. So we can summarize that we have managed to construct a probability law on the collection of continuous paths which has the right finite dimensional distributions, and therefore we have shown that there actually is a model for Brownian motion as a limit point of this diffusively scaled sequence of simple random walk on the integer lattice.